Okay, today we're going to look at Garfield's method for solving the Pythagorean theorem. In order to do that, I had to construct a trapezoid which is built with three triangles. The first triangle here on the bottom with sides A, B, and C is a right triangle, and I also reconstructed that triangle over here and then joined the top vertice and the lower vertice together, forming another right triangle. But before we talk about the theorem, we should really convince ourselves that this angle here in the middle is a right triangle, is a right angle as well. And the reason for that is because all three of these angles have to have a sum of 180 degrees. And we know that in a triangle, all three angles have to equal 180. So if we look at the bottom triangle, angle 1, angle 2, and this 90 have to have a sum of 180 degrees. The same angles are listed in this top triangle as well. So angle 1 and angle 2 plus 90 degrees, angle 1 plus angle 2 plus 90 have to have a sum of 180. If we take away 90 from both sides, we see that angle 1 and angle 2 are equal to 90 degrees. So looking at this area, angle 1 plus angle 2 would have to be 90. What's left for angle 3 to form 180 degrees would have to be 90 degrees. So angle 3 is also a right angle. Okay, getting to the proof. First, we look at the area of a trapezoid. The formula for the area of a trapezoid is 1/2 times the height times the quantity base 1 plus base 2. Also, if we try to find the area of this trapezoid, we could find the area of the triangles separately and add them together. So the area of the trapezoid would also equal the sum of the areas of the triangles. So that the sum of the area of, let's call this triangle ABC on the bottom, plus the triangle of, let's call this one triangle CDE, and the area of triangle ECA. Okay, so let's start with the area formula for the trapezoid. In this case, we have the height, but the height is represented as the sum of sides A plus B. So I'm going to substitute the quantity A plus B for the height. And then we look at base 1. In this case, it's side B. And then base 2, which is the top base, is side A. Now, using some algebra, we can simplify this equation. Okay, here I can reorder the terms. I can, instead of writing B plus A, I can rewrite it as A plus B. That is the commutative property of addition. And then performing what's called the FOIL method, or distributing the A plus B to this other quantity, A plus B. And we will end up with A times A is A squared. A times B is AB. B times A is BA. And B times B is B squared. Okay, again, we're going to use the commutative property, and we are going to rewrite the term BA as AB. because the commutative property with respect to multiplication allows me to reverse the order of the variables. And now we have two like terms, AB plus AB. And we can combine those like terms into 2AB. Okay, at this point, I want to look at the area of the trapezoid by looking at the areas of each of the triangles combined. Okay. So, the area of a triangle, the formula for that is 1/2 the base times the height. And if we look at triangle ABC, the base in this case is represented by side B, and the height is represented by side A. With triangle CDE, the height in this picture is side B, and the base is side A. And finally, the last triangle, triangle ECA, we can call side C the base and also side C the height. So we end up with 1/2 C times C. Okay, and then simplifying this, it's going to be 1/2, and again I'm going to use the commutative property and turn BA into AB plus 1/2. Do the same thing here, make that AB, and then 1/2, and C times C is going to be called C squared. Okay. Now, since the area of the trapezoid is equal to this 1/2 times the quantity a squared plus 2ab plus b squared, but the area of the trapezoid is also equal to 1/2 ab plus 1/2 ab plus 1/2 c squared, these two must equal each other. So I'm going to bring down this part here and set it equal to the previous c squared. Okay, and then we're going to use some algebra to clean this up. Okay, so what I notice is that each one of these terms has 1/2 in it. So I could essentially factor out a 1/2 from each one of these terms. And I'm left with AB plus AB plus C squared. And I'm just going to recopy the left side here. So it looks uniform. Okay, and now when we try to solve an algebraic equation, we can get rid of the 1/2 by multiplying each side by the reciprocal of 1/2, which is 2. So 2 times 1/2 will cancel out, and 2 times 1/2 over here will also cancel, leaving us with a squared plus 2ab plus b squared. And on the right side, I can combine these two terms together. 1ab plus 1ab is 2ab plus c squared. And then, using the subtraction property of equality, I can subtract the term 2ab from both sides of the equation. And we're left with a squared plus b squared equals c squared. And hence, the proof of the Pythagorean theorem.